Hi, everyone. Welcome to Async. Welcome especially if it's your first time here. Async is a monthly meetup. We meet on the first Thursday of every month. You can find out more about us at async.com. Oh, and also hello to live stream viewers. Do we have live stream viewers? Cool.
Not yet.
Cool. Well, hello to potential live stream viewers and the ones who rewound to see the whole thing. We have a code of conduct. Usually I'd have slides up here, but we don't today. So I'm just going to tell you. You can go to async.com and you can click to see the code of conduct. It's fairly standard and very simple. You know, be good to each other. Try not to do things that gonna make people uncomfortable. If you are made to feel uncomfortable by anyone, please come and talk to me or to Cameron, and we will try and do something about it. I would encourage people to go read the code of conduct. It's not very long. Today I want to thank Silicon Brighton as always. So Silicon Brighton are an organization that supports a bunch of meetups in Brighton. They have been absolutely invaluable for Async. You know, we're otherwise entirely a volunteer run, and yeah, everyone has lives, and it's difficult to keep it running. It's usually run by people like Alistair and Jan, who still do huge amounts of work. I do basically nothing apart from occasionally come and do this bit. Silicon Brighton also supplied the beers today, and of course, yes. and thank you to Cameron for doing the audio-visual support. So I've got a microphone, so I don't have to yell, and we're being broadcast on YouTube, which is pretty cool. Go check out Silicon Brighton if you want to see other stuff that's happening. Also, thank you to Runway East, this place. So Runway East are a co-working space, and they do office rental. It's obviously quite a nice place, as you can see, because you're here. They also supplied us with the pizza. So thank you, Runway East. Tonight I want to introduce James. So if you've been coming to Async for a while, you probably have met James before. He is probably one of our longest running members. He's been coming for a very, very long time. I believe he's probably given one of the people who's given the most number of talks as well. I don't think we've been blessed with a James talk for quite some time. We were trying to figure it out earlier and we can't remember. So many of you have not seen James talk before. He's very, very smart, and he does very interesting things, and you're going to see that. So he's going to talk about building a bridge between Rust and React Native. So I'm sure he will tell you all about that. I think that's everything I meant to say. So I'm going to introduce James. Oh.
You do. So, hello, I'm James. We've got a sound check. So, welcome to my 6th talk. And the first talk was in 2012, as you can see. This is the web page as it stands today. This is in a little iframe. Gave this talk at Bletchley Park. I gave it at an iOS conference. I gave it at an Android conference. And I even went to India with it. So does anybody want to know what it was about? Does anybody want to know Précis? Yeah, cool. Okay, in 2 slides. So, mobile development is really, really expensive. This is 2 mobile apps, an Android app and an iOS app, and it was then an iPhone app rather than iOS. It was, so we needed to make it cheaper somehow. But PhoneGap, which was the WebView-based technology, made really, really crappy UIs, really crappy user interfaces. So we needed something to do better. And so my idea, and the thing that I took all over the place, was why not share the business logic, put business logic in a common piece of invisible JavaScript, and then build native UIs on top of that. And yeah, that's the end of my talk. Thank you very much. So 2015, that was 2011, not uncoincidentally, 2015 heralded the release of React Native. So common business logic in JavaScript, but they went one step further, and they put React and a very clever bit of code which was rendering native UI components by essentially JavaScript. And today in React Native, it looks approximately the same in this ridiculously simplified schematic diagram. And you see that we've got TypeScript rather than JavaScript, and we've got Swift instead of Objective-C, and we've got Kotlin instead of Java. So and during the meanwhile, in native land, roughly the same sort of story. There was Swift and Kotlin was really the only thing going. So during my time, so over the years, that sort of idea of getting common SDKs, getting common business logic into multiple different platforms has sort of spread. And so, and the language choice at the moment is Rust, really. It's we'll come to those the reasons why, and the two are sort of merging, and this is what today's talk is about. It's about these common Rust SDKs, but instead of being in native apps, they're now in React Native apps. And so the talk is going to be roughly about this line here, and bridging between TypeScript and Rust. Okay. So who am I? I'm James Hugman. Hello. I'm a software engineer. I was at Mozilla until recently for about 11 years, and worked on a bunch of apps with a bunch of languages, but mainly I'm sort of the back end of the front end in mobile. That's where I'm most comfortable with. And there's loads of really interesting problems there. So let's talk about React Native. So yeah, in 2015, it was write once, learn everywhere. And the joke at the time was write once, optimize everywhere, which was better than the previous joke, which was write once, debug everywhere. But yeah, so it shipped with JavaScript core, which was the JavaScript engine, which is available from WebKit, and Apple, I think, maintained that. And every single app shipped with this massive blob of C++ called JavaScript core. And it was slow because calling out to native was always asynchronous, and you were doing a lot of calling out to native because that was where the UI was. And it was very heavy because it was optimized for web pages. So very and sort of web pages you spend a few seconds on and then you move on to the next web page. This was massive apps, and so the startup time was very, very important. Yes, so and then this too heavy bit, it's very heavy, didn't need a lot of it, and it had very big APK sizes and app sizes. So Facebook haven't sat on their hands, and they've done something about this. So this is what they've done. It's a new JavaScript engine called Hermes. If you're a React Native developer, you will have heard all about it. But for the rest of us, it's written in C++. It's a virtual machine, and it runs. It also comes with a JavaScript bytecode compiler and an interpreter for for debugging and development, and also crazy, an experimental TypeScript C compiler. We can talk about that later on, but I haven't got any slides for that. And there's no event loop, and there's a C++ JavaScript interface, a JSI, and currently, and this is, I haven't found any documentation for this, but this is what I think I've found, is that it's not actually a standard, it doesn't run any kind of JavaScript standard. It and Metro, the bundler, provide enough simplification. So there's a sort of source-to-source compilation and then another source-to bytecode compilation. So, but that's apropos to this story, not really relevant to this story. And this is the slide which I took off the React Native blog post on Hermes. It shows, why do all the parsing and into bytecode at runtime? Why not do that before you install it, as in before it ships to the App Store? So Rust. Not really a talk about Rust until you introduce Rust. So Rust is a modern systems language. It emphasizes performance, safety, and productivity. And in sort of non-marketing speak, it's a compiled language compiled with LLVM, and it runs as fast as C because it's compiled with LLVM. It runs anywhere that C can, but it's much nicer and safer to work with. And these three, the run anywhere C can, is really the most interesting thing for me. So what about bridging to JavaScript? Well, we'll come back to that. But I just wanted to define a term, so foreign function interfaces. This is this, Wikipedia defines it as a mechanism by which a program written in one programming language can call a program compiled in another language. So this is the foreign language bit, and foreign function, we know what a function is and we know what an interface is. So it's the sort of where two languages meet. And it's commonly called a bridge. So this is why you see all these bridge photos and metaphors. And uniffi, which is what we're talking about today, is a project started at Mozilla, and it's a multi-language bindings generator for Rust. And so you'll see these bindings generators, bind gens, all over the place, including in this talk. But I just wanted to define bindings generator, bind gen. So okay, and it's pronounced uniffi and uni1fi FFI. So okay, so it started off with just Android and Swift, Android, Kotlin, and Swift for iOS, and then Python was a good testing language, and then somebody just turned up one day, just went, here's Ruby. So now Ruby is part of the official distribution, and then the third party, other people have just turned up and contributed all these different languages as well. So in various different states, these are all available. And so apart from Mozilla, who's using uniffi, and I just wanted to, Mozilla's using it in Firefox for Android, iOS, and desktop. And I recently heard that Google have started using it in Android itself. So they're starting to use a lot of Rust in Android, and that they want to provide Kotlin bindings. So they're just using the Kotlin bindings. And Bitwarden, so they make a password manager, and NordVPN, they've done an awful lot to contribute. And Element, who's heard of Matrix? No, yeah, great. And then there's a handful handful of other projects. YRS, which calls back to Dave's talk last month, and Lottie, the Lottie RS, and then a whole bunch of crypto things like the rest of Rust. There's a massive long tail of crypto bros. So we're going to see this diagram a lot, or variations of it. So this is roughly how it works. This is unified by nodejs Swift, and you've written some code in Swift, and you want to call some Rust, and so you call this generated bit of Swift here, and this is with it's a high level language, and you've got high level types, and then the first step is to lower it down into a low level types. And the reason for that is because you want to get it across this C boundary to Rust. And then Rust does the opposite. It lifts these things from low level to high level types. And then, so this is all generated. And then the librs is what was written by the Rust developer. So everything in these boxes are generated. And this is the Kotlin one. Looks pretty similar. It is very similar because I cut and paste the same things here. So these the Rust is the same throughout, whether it's Kotlin or Swift or whatever. The Rust is always the same. Okay, but what about JavaScript? I hear everybody call, because this is a JavaScript meetup. So, and to which I say, but which JavaScript? So we've got a whole load of different types of different places JavaScript can execute. So the browser, different. There are different implementations of that. Node is V8 and Electron is V8, and then Tauri is also a sort of, I don't know, whatever the browser is. And then there's a whole bunch of these, including our lowly Hermes down at the bottom. And then here are the mechanisms that you get into the various target machines code that you've compiled your Rust to. And so yeah, okay, so we can go home now. It's all done. All these boxes are filled. Splendid. But okay, so here's the first problem. WASM. WASM in a browser is amazing. It's a virtual machine though, and that virtual machine is designed to be sandboxed. And at the moment, that virtual machine is not as powerful as the machine that you have, when you're running on bare metal. So it has no threads. It's probably not got access to the file system. And if it is, then it's async access to the file system. And it's a sort of, it's a simulated access. And the worst is that if you've got your SDK already written, and it's not already written for WASM, then maybe that'll work, but it might just not run. I mean, it might not compile, and that would be bad, but also it might panic. It might compile, but panic at runtime, which will be even worse. And React Native support is kind of in peril now. Ask me about that later. Oh, no, I can just tell you right now. The guy who's written the WASM 3 interpreter is, he's got a thing on his blog post, which on his GitHub, which is, because Russians have invaded my country and destroyed my house, and then you can fill in the rest. And then problem 2 is that there's no sort of standard ABI. So an ABI is a low-level interface between programs, and C is the lingua franca, it's the common language. So if you speak C, then you can speak to all the other languages. But unfortunately, every language has its own implementation, and JavaScript there is no, there's no standard for that. So this is a bit of circular. So this is, but as I said in slide 12, Hermes has got its own C++ JavaScript interface. And so this is, and this will be the last bit of C++ you see today. This is adding a function, an add function to the global context. And here are the arguments. And we're just going to add these in a loop and then return them. So this is all what the JavaScript engine sees, what Hermes sees when you write that loop in JavaScript. So there's no sort of FFI here. This is actually what is how JavaScript is implemented. So now we've got all the pieces to make a unified bindgem for React Native. So back to this diagram. So we've got TypeScript calling into a generated blob of TypeScript, and then we lower the types into, we'll come to that in a minute. And then we call into JSI, into this C++, which then lowers it further and pushes it through the C interface into Rust, same Rust as everything else, and then Rust lifts it and then calls the client-facing code. And so we're starting this, we're building this bridge, and we need to get to four directions. So we build one on top of the other. So we start with calling from JavaScript to Rust, and then we go from Rust to JavaScript, and then we do the whole thing again, but async. And then for each direction, we need these three things. They're all, I'm saying types, but it's types of arguments and a return value and errors. So for those are the arguments, and that's a string. You might return a string, and here's an error that you might throw. But that's all in JavaScript. So first direction, JavaScript to Rust. This is what the TypeScript developer will write, and this is what the Rust developer will write, and everything else is generated. So I'm just going to call greet in JavaScript, and you end up calling Rust, the greet function in Rust. Rust to JavaScript. Well, we've defined this this interface, which is a trait in Rust, and that defines some methods, and then you have a class which you define whatever the callback is going to be in the class, and then you pass that callback interface object to a method, and then it then calls back into the JavaScript that you just defined. So this is where it starts getting tricky. So JavaScript to Rust, but async. Building on the other two. So we want to await this async function in Rust. So we call that, and that sleeps for however many seconds, for 1,000 milliseconds there, and then returns. And then this requires quite a lot of setup, but it's very simple after you understand it. So this is the callback function, and you pass it in like you do for the non-async version, and then if you see this, we just have a promise here, which is set timeout, and then it logs this message, and you just await this. Okay. So, and we've talked about arguments, return types, and errors, and what sort of types can they be? So, so simple. We've done this a lot. Strings, unsigned integers. That's integers without that are positive. Signed integers. So all of the numbers, and floating point. So all represented by numbers. These things, and then 64-bit integers. So these are integers that are represented by by 8 bytes. So can get really, really big. And oh, TypeScript has got a big int apparently. Who knew? Who knew? Anybody know? No, nobody. So most most numbers allow for 53 bits for their integers, and so the max safe integer is 2 to the 53 minus 1. You can't actually do that sum with a number because you overflow the numbers when you do 2 to the 53. But big ints can do arbitrarily large integers. That's like, holy crap, that's amazing. So, and the syntax is really simple. You have this constructor here, which takes sort of the same things as numbers. But you can also have this n notation as a literal. So you can, and it works with all the existing operators. So here's 2 to the 53 minus 1, sorry, which doesn't overflow. So yeah. Holy crap, that's amazing. Structural types. This is option type. So that's something in Rust you have option type, but in TypeScript you just represent it as T or undefined. Could be null. I chose undefined, but sequences, just arrays. Maps, which are maps of key to value, and then enumerated types. So we've just got, who knows about enums in TypeScript? Okay, very simple. They're just like Java enums in TypeScript. Okay, and tagged union types, which Dave is fist pumping there because so yeah, who knows what they are? Dave, yeah. All right, so so tagged union types. So this is an enum in Rust, and you can have a variant that is just like Java, just like JavaScript. No, JavaScript doesn't have enums. Haha. TypeScript enums, and then you can have values with them. So unnamed values and then named values here. And these are amazing for what's called pattern matching. So you put, you say we've got this, this area function here. You match on the shape and whoa, it's a rectangle. And so now you're able to destructure this length and width straight from, straight from the match, and then you're able to deliver a calculation based on what shape it is. Cool. So is that available in TypeScript? Ooh, maybe, maybe not. Probably yes, it is. So you can use what's called, I think it's a discriminator, discriminated types. So my type theory is not great, so forgive me if I get the language wrong here. So, so you define your union of different type shapes, and you define a discriminator, called a tag, in another type. And so, and then the TypeScript compiler does the rest. Amazing. So you do a switch instead of a match on the tag, and then you match on that tag, and then the TypeScript compiler knows that shape.inner has this length, width, and color. And then you can just unpack that inner, and then you return the length times the width. Cool. Okay, so objects and classes. These might be a little bit harder. So we call them records because of, I don't know, legacy reasons, but they're objects without methods. And we've got objects which are class objects with methods. So, so the first one, records, we've just got, we have pass by value semantics. So if you got, sorry, excuse me. So you make a copy going from JavaScript to Rust, and you make a copy going the other way around, Rust to JavaScript. But we've got this little wrinkle of the Rust compiler, and this is in the weeds. But so yeah, so we've got this the same thing here, the same shape of struct in TypeScript versus Rust, and then we pass that method from one to the other, and it just turns up. So, and then the important thing is every field is serialized to across the FFI, and so once you've given it away, then it's the previous one is the one that you've just given in one language is, well, they're yours to keep, or it's destroyed. So, and then objects, that's with methods, they're passed by reference. So you get the pointer passed back and forth as you call the methods. So you get a live object on the Rust side, and that can you just look after that in JavaScript, and it just calls back to the same object. And so the switched on people in the audience will be interested about garbage collection. So what happens when the JavaScript version is garbage collected? There's no garbage collector in Rust, and you've got to keep them in sync. So another today I learned in JavaScript, finalization register. Who's heard of this? Only because Tom and I had a right. Okay. Yeah. So finalization registry, that's a callback that you request to get when something gets garbage collected. So you have a finalization registry per type, essentially, and in that I will call back into Rust with that particular Rust handle, and then I will register that in the constructor of my generated type. But yeah, so that's that. But there's some semantics. So we've got this. I can't remember what it's called, but it's all the books say that you should leave an explicit function for you to call into, just in case the user wants to get rid of it immediately. So so we've got a unified destroy here. That's added to every object. But you want to stop that being called twice, or you want to stop the my object being called twice. It mustn't be called, because that's a security hop. So you can, once you call that, then unregister gets takes this out of the registry, so it doesn't get called. The callback doesn't get called when garbage collection. Is that everybody happy with that? Yeah, nods of heads. Good. But it's not supported by Hermes. So again, ask me later how I did this. So I've talked a lot about lifting and lowering, and we've talked a lot about what the high-level languages are, what the types are at the high level on Rust, in Rust and TypeScript. And so now I just wanted to briefly talk about this C API. So I'll give you an example. JavaScript function is called with a string argument. The JavaScript function is implemented as lower the string into an array buffer, and then an array buffer is called is passed along across the C boundary. And then on the Rust side, it's caught by Rust as a byte array, and then lifted into Rust into a Rust string. Okay, so you've got this common language of a byte array. So today I learned in JavaScript, there's this array buffer thing, which, who's used an array buffer? Yeah, Tom? Yeah, oh wow, okay. So about half the audience know what this is. So you get an array buffer. It's a fixed size of a fixed byte array, an array of fixed size, in this case 9. And we're going to have a view on that, which we're going to write and read stuff out of. So we're going to write, and in this case, we're going to represent an option of F64. So that's in TypeScript land, that's a number or an undefined. And so we're just going to do this check whether it's not undefined, and say that there's a value if it's not undefined, and then here is the value. So we've got these setter methods, great. And then if not, then we just set this byte as a 0. So we've got this serialization protocol going on. And then the read is the same. I mean, it's just in reverse. And these views have got these amazing, I mean, I say they're amazing because they are so much more ergonomic than using typed arrays for this, which, well. Right, we're going to do that in code now. All right, bear with me here, because this is going to get really, really nitty gritty. So, and I expect cheers at the end. All right, so we've got this this code here. We're going to start up here, and we're going to go again. It's this U-shaped motif that we've been using. So we're going to call create greeting. Now that's going to call some TypeScript, and that this is generated TypeScript, and we've got create greeting who, and then we're going to lower that into an array buffer or whatever it is, and then who underscore, the underscore in this example signifies it's a low-level type. Okay, so and then we're going to go return value, the low-level return value. And we're going to call across into Rust by C++. So now we're in this this Rust, this low-level Rust function, and then we're going to convert that into from an underscore, a lowered version, to a raised version, a lifted version, and then we're going to call the actual code that the Rust engineer wrote, which was create greeting. Now, if you'll notice this create underscore greeting in Rust and create greeting in TypeScript, that's all done for you. It's all done automatically. So then we get hello world, or hello who, and then we do the whole thing in reverse. We go back, we lower the return value, and then we receive that in the generated TypeScript. And then we lift the return value, and then we get to the end, and then who knows what it's going to be? Hello, Async. Yay! Tepid response. Great. All right. So, demo. That's all very well in slides. Do you want to see that live? Yeah. Okay. All right. This might take a couple of minutes to set up. And okay. So, all right. What have I got here? So, all right. Oh my God. Oh yeah. There we go. Doing EMs. All right. So Android or iOS first? Android. There we go. All right. So this is the sort of the control. All right. So here's the app. So compiling. This is yep. Oh. Great. So look, result 42. Great, yay. So that's thank you. So now I'm going to do that in iOS. What I'm going to do is I'm going to make a change in the code, in the Rust code, and then see it reflected in TypeScript and then run it in the TypeScript. Oh, what? Okay. Sorry, say again? It's booted already. Oh, yes. Now, yeah, I found in this particular incarnation, iOS just needs a little poke from Xcode sometimes. So who has anybody else seen this problem in most recent versions of React Native? No, all the experience React Native. I'm not a React Native developer. Oh. Oh well. Okay, no. Okay. All right. So we've got a bunch of things to do first. So the first one is we're going to get rid of this. I'm going to type with one hand. So, oh my goodness me. Result equals create. So, well, what I was going to show you was this not being here. So, and now it is here, but I'm just going to use a second message, second thing, because that shouldn't have been there. So, all right, create greeting message 2. All right. So I'm just going to look for that here. Oh no, there's only create greeting message 1 here. So let's, all right. So I'm going to call yarn, ubrn. All right. So this is calling a command line app written in Rust, which is essentially looking at, it's compiling this Rust for I think this is iOS. Did I say it? Oh yeah, Xcode's bouncing. So it's compiling it for iOS, and then it's rebuilding the bindings, the JavaScript and C++ bindings. And so I'll do the same with Android. So what's going to happen here? All right, so that is that's that. So now I want to, oh, look, create greeting message 2 is just there. And so I don't have to faff around with array buffers or extern Cs or anything like that. And so now I'm going to run this. And what do you think it's going to say? What do you think it's going to say? So this is iOS. I might need that poke again. The simulator is hopefully showing itself, but it's not going to without any help. So you can see the edit compile run cycle is very slow, very slow. And so what you end up having doing is using Rust's excellent facilities for testing to do a sort of test your SDK at the Rust layer and then generate this. Oh, look at this. Yay! And then do you want to see it on Android as well? Yay! So on Android, yeah, you use the Rust, you test at a headless level. And so you end up, if you're developing in a team, you've got the Rust engineer building loads of really high quality stuff because it's well tested and it's easy to test and it's fast and what have you. And they hand it over and then you do whatever you need to do with it. So, but you generate, you end up with a library that looks like a JavaScript library, not having to deal with the complexities of bridging between the two. So, yay! Look, it's worked with Android. Cool. So, oh, that's my calendar. So that's the demo, and I think that's thanks very much.
Hello. So I think you might have hinted at it earlier, but I was just interested to know your thoughts on static Hermes. I think it might be hinted at in the beginning.
Static Hermes. I haven't seen very much, and I've looked quite hard for things, and it looks like a bit of a science project. I saw the talk at ReactConf by one engineer, and then there was another blog post by that same engineer. It looks amazing, and I hope it sees the light of day. So for context, this is static Hermes. This is the TypeScript to C compiler, and it also comes with these amazing facilities to write FFI code in TypeScript. So you're calling whatever Python or Rust or C straight from TypeScript, and it compiles it down to source-to-source compilation into C, and then uses I think LLVM or whatever. So if it sees the light of day, that would be amazing, and it would pretty much reduce the need for anything like this, or it would substantially change it anyway. Yeah.
Ooh, do we have another question? Oh, nice. Okay.
Someone's got a filler question. That'd be great.
I will get my phone out so I can read the question out.
Yeah, you mentioned garbage collection earlier.
Yep.
So is that for if the Rust program keeps state, like when? So because obviously, if you're just passing something to the Rust program and then getting it back, the garbage collection is that important in that case? And does the Rust program keep state? Is that even possible with the unified model?
Yeah, absolutely. I mean, what we were using in Mozilla was you call into Rust. The Rust then downloads something. It might stash something in a database. It might keep stuff in memory, and then returns, and then you then query whatever the database or whatever's in memory. So yes, there's definitely scope for state in the Rust. The garbage collection is what happens when I don't know, you've got an image on one side of the FFI, and you don't want to keep shipping it back and forth, you're finished with it in TypeScript, and so you want it to be destroyed in Rust somehow. So JavaScript has this garbage collection, and Rust has a very different set of semantics around memory, and so you're really wanting to listen for that garbage collection in JavaScript, and go, well, if it's ready to be destroyed or freed up, then Rust needs to know about it so it can actually do the freeing. The memory is held in Rust. Does that answer your question?
Yeah, I mean, does that cause the potential for a runtime panic in Rust? Because obviously, if Rust thinks that it's not needed anymore, then it would destroy it anyway. So if the semantics are in Rust that it's keeping that memory around because it thinks it might need it, does that cause a possible runtime panic? Or
no? So the Unify provides the bookkeeping that it has a reference counter essentially, and the reference counter is incremented and decremented whenever you use it in JavaScript, and then when that reference count gets to 0, the memory is freed.
Okay, cool. Thank you.
No worries. I thought you were going to ask me how I did it, but
I would like to hear that, but
Yeah.
I'm going to ask a question from chat first.
Okay.
So Jan asks, you mentioned a lack of synchronous APIs, e.g. for files, as a negative in a handful of places. Why is this negative? Or you can make async calls. So why is async bad? Saying to the async audience.
It's not bad per se. It's just some libraries, some Rust crates are written with synchronous file access in mind. So if your aim is to not change your Rust because somebody's already written it, then synchronous file access has to happen because it's there already.
Well, that makes sense. Jan says, "Oh, I see." So,
great.
Dave.
Something just occurred to me when you talk about async. This is basically my lack of knowledge about Rust. So in TypeScript, you've got this promise type, which is sort of a blessed thing.
Mm-hmm.
I noticed that you can do async functions in Rust from your slide, and I didn't know that was possible. And how does that work? Is there also a blessed promise or future or whatever type in Rust and library, or because I know people have different async libraries in Rust. I just wondering.
Yeah. So there's a future trait, and then different implementations of that future trait exist, and so yeah, it works in a very different way to how JavaScript works, but you end up using it in the similar sort of way. Does that make sense?
Thanks.
When you mentioned the big int, what are the benefits of having that? Have you run into any problems where you've needed a bigger integer value?
When you need a bigger integer, yes. I mean, you can, if you want to represent, say, pointers, which is how this works, how it works at the moment. You want to be able to represent 64-bit numbers, because that's what your address space looks like. If you are doing things with science, then how many stars in the universe?
Yeah, that's kind of what I was thinking about. Yeah.
Then also the other big use is cryptography. So you're dealing with very, very large numbers with cryptography, and you want something which is which is blessed by the JavaScript engine. So,
cool. Thank you.
No worries.
is actually just an additional answer to that question, which is I've dealt with it in trying to get numbers across from Postgres into JavaScript, and Postgres can support big numbers like that. You might use it on an ID field if you've got a really big table.
Right.
And,
Yeah.
If you end up with IDs, having huge jumps because they're being stored in a 53-bit number, that's not good. So
Yeah.
I've actually written a JSON parser before that can handle that and
Wow.
handle it into big int. And I think that might become a standard at some point.
It has. It's already
Yeah.
a standard. Yeah.
So you're saying that 53 bits is not enough for anyone?
No,
Has
Bill.
anyone else got any other questions? Cool. I would love to hear how you got around the lack of the the registry in Hermes, the DC. Is that a question for now, or is that a pub question?
I can answer it in a few lines, or even a few words.
Let's do it then.
C++ destructors. So
Wow. Okay.
yeah. So you have a special object in C++, which I implemented, and you give that special. You give it essentially a callback, which you're going to call into Rust.
Okay. Yeah.
And that's
So-
all done in C++.
So the JavaScript objects are actually C++ objects, which Hermes can see as JavaScript objects, and then you get to do the C++ thing. Cool. Okay.
Yeah. So when that object is garbage collected, it just gets destructed in C++ land.
Yeah.
It's not a complete analog, but it's good enough.
Cool. Nice. Any other questions? Cool. Okay. Thanks so much to James for the talk. Let's have a round of applause for James.
Thank you.
So we usually go to the pub after this. So we go to the, what's it called? Unbarred. There's the one. Yes, so Unbarred. So it's just around the corner. So we'll get someone to lead the way and go there in a minute. So yeah, please do feel free to come join us there, or to come join us the next async. So apart from that, I don't think I've got any other things. Earlier I mentioned Ali and Jan as being the backbones of async, and I should have also mentioned Jake. I've been thinking about that the whole talk. He also does a lot. So thanks to Jake as well. Yeah, and thanks to all of you for coming. And yeah, we'll see you next time.